Howdy. So this is my final project for FEA. I wanted to do a dynamic analysis of a strap, a cargo strap, and kind of investigate what the effect of twisting that strap has on the overall vibration at given frequencies. So if you're ever driving down the highway, you'll probably see cargo trucks usually when they strap something down to the trailer, they'll put a little twist in the strap, and that's supposedly done to keep the strap from vibrating at higher speeds. And not doing so can cause that cargo strap to shake violently. So, um, to get started here, I did a couple, actually three models for this project. So the first one here was just a beam. So I wanted to analyze the strap using beam elements. Started off here with just a wire. The second model here is actually a shell done directly here in Abacus. This is just a flat surface essentially. We gave it a thickness later on. But yeah, just a shell that we did to model the essentially flat strap. So and then the third model here was actually a strap with that twist in it. Essentially modeled this as a surface in SolidWorks, imported it into Abacus, and then I was able to assign thicknesses and things like that to it, just how you would with a shell. So going to the material properties, we've got polyester webbing is what they're typically made out of. So density here and Young's modulus is really all we're looking at here. And this is the same material across all of these models. So in our step module here, for each of these we have 4 different steps defined. So we have the initial step, then we have this tension strap step, and so this step is where that tension is getting applied in the positive y direction here, this reference point. I also have this frequency step, so this is how I actually got the natural frequencies of the models here. And then the dynamic flap, this is just a dynamic implicit step, essentially where we're applying loads and things like that to kind of simulate the aerodynamic forces that would be acting on this. So, all right, so going into the load module here, with each of these, I have this distributed force. Then we also have a moment that's acting right here at the center. So that's giving it that kind of torsional response. So the other thing is those forces are acting in the dynamic step here. Then we've got this tensioning force acting on that reference point. That comes into play in the tension step. So as far as boundary conditions, we've got these boundary conditions down here. So this bottom edge is just fully fixed. This is if you were to tie this down to a trailer, that bottom edge wouldn't be moving ideally. And so this is all fixed, all degrees of freedom there. And then at the top, on the reference point, we have all of the degrees of freedom fixed as well, except for the displacement in the y direction. So for the beam model, instead of having a pressure right here, I did do so this is a distributed line load. As I mentioned, we did three different models. So the beam model here is of course just meshed with beam 3B31 elements. So just 3D beam elements. Each one has 6 degrees of freedom, 2 nodes, and then the other ones we've got here are the meshes for the shells. So both of these are meshed with S4R elements. That's just a 4-node shell element that each node has 6 degrees of freedom. So here we have different modes, different frequency modes here for the beam. So The one that I actually went with was mode 3 with all these. This most closely, I think, resembled the flapping that we were trying to get to here. Frequency here is 3.3242 hertz. Frequency for the untwisted S4R. Here we have the third mode for that. And similarly, we have 3.3454 hertz. So here we have the frequency mode 3 for the twisted strap. The frequency is 6.183 hertz. So what you can get from that is that essentially twisting that strap increases the stiffness of this strap, right? And so the natural frequencies here are actually dependent on the mass and the stiffness of that object. And so since we're not changing the mass, we can tell that twisting it does indeed cause it to become stiffer, which is going to increase that natural frequency here. So here we have the flat strap shell elements being flapping around in the dynamic step here. And you can see that flapping here is pretty significant. So main reason for that is that all of these, I was applying a load, those distributed forces in the moment I was applying them at that harmonic frequency. And so you'll see with the flat straps, since they're both relatively close for that mode 3 frequency, we are very close to harmonic resonance. Now just a little bit more here into how I actually applied these forces at those harmonic frequencies. So here there's a little amplitude that you can create, and creating this amplitude, you can take the circular frequency here. 2 pi f is essentially the conversion from your that natural frequency in hertz to a circular frequency. So that's essentially causing that force to oscillate back and forth, which gives you those different forcing conditions on the strap, as kind of simulating wind. Here we have a plot of that displacement for the displacement versus time for the beam. And when we compare that to the flat version of the S4R model, we get very similar profiles. So both of these experiencing harmonic resonance, causing that amplitude to grow. Now, if we compare that to the displacement of the twisted model, see that our displacement here, max displacement, goes from 1 all the way down to below 0.04. So it makes a significant difference in that displacement along the x-axis. And then if we're looking at the rotation as well, we get a decrease in there. So with the beam and the S4R flat model, we get very similar profiles again. And then once we get down to the twisted model, that one itself drops down from about, I guess, 0.6 radians down to roughly 0.45 radians. And then finally, looking at the peak von Mises stresses throughout these straps, we can see with the beam model that our peak stress here is about 9.4 times 10 to the 7th. Twisted strap here, that we actually see that von Mises stress drop down about an order of magnitude here. That's mainly because as this thing is more stiff, we're not seeing as much deformation in the strap itself, and so we're getting a lot less stresses in the middle and up here at the tips. So overall, this project was a lot of fun. I think when I started this, I was a little bit curious as to whether or not this would actually be possible without doing any sort of CFD or anything like that to model the actual airflow. But I think, as you can see here, it is possible to kind of approximate those aerodynamic loads using just moments and distributed forces. So Anyways, thank you for watching.